clearly understood. I would like to start with some examples of circular motion again. And these are familiar examples. For example, example 1 is about a stone tied to one end of a string and whirled around. For example, this is where you are holding the string. This is the hand, and this is where the stone is, and this is how you are whirling it in a horizontal side. And the length of the string is the radius of this circle. The familiar example. Another example of circular motion is a car taking a turn. It may be a horizontal road like this, on which a car is moving away from you. You are seeing it from behind, and the car is moving in this manner. And this may be the radius of the circle in which car is moving. It could be several kilometer large radius. Then a very commonly known example of circular motion is a planet going around the sun. You have sun here with a huge radius in which a planet is moving. So this is yet another example of circular motion. These examples will make the basis for further discussion in coming chapters, in which we talk about the gravitation and the centrifugal forces which are responsible to make these circular motions happen. Another interesting example of circular motion is that of a charged particle moving in a uniform magnetic field. You have already learned in your O-level classes that if we apply a magnetic field into the page, into the plane of this board, for example, and a charged particle enters into this region in which magnetic field has been applied, this charged particle, if it is a positive charged particle, will follow a path like this. And ultimately it will go on in this manner, if this region ends here. So this portion is the circular path that the charged particle has followed. So this is an example in which charged particles are moving in a uniform magnetic field perpendicular to their motion. Another example that we discussed last time was that of a pendulum. If I suspend a pendulum in this manner initially, then I displace it from here and push it away, it will start moving in this manner. So this is again a circular motion in the horizontal plane, and this is the radius, which is basically the displacement of the pendulum from its knee position. So it moves on in this manner, executing a simple harmonic motion. Another example on which we have a question in the Cambridge, and we'll discuss that question in detail in the next few lectures. This is a large ball like this, and there is a marble initially placed here on one side of this ball. When you push it away from you, it starts moving in this manner, remaining in contact with the sides and executing a circular motion. And this is obviously the radius of this circle. The radius of this circle will depend where it was initially placed. If you place it above, close to the brim, this will be a larger radius. If you place it somewhere close to the bottom of this ball, the radius will be smaller. So the radius depends on where you started. Similarly, another simple example was that of that of a coin. For example, this is a disc, and this is the axis about which it is rotating. This is a disc, it is rotating in this manner about an axis, and you place an object here. It may be a small coin of certain mass m. When this coin, when this disc rotates in this manner, the coin obviously moves in a circle. And this is the radius of the circle, which is the distance of the coin from the axis of this disc. Similarly, if you consider yourself, assume yourself to be on the equator. For example, this is the Earth. This is the Earth, and this Earth is rotating on its axis in this manner, and you are here on the equator. So, anyone on the equator will be moving in a large radius, making a circular motion. And if you move above the radius somewhere close to the pole, like this position, your radius will become smaller, but you will still be moving in a circle. This is a circle. If you are here at the equator, the circle is very large, and the radius is exactly equal to the radius of the Earth. But if you move above this, closer to the pole, your radius in which you move now is smaller. So this is the radius. In all these examples, angular speed remains the same. I'll highlight this in a few moments when I talk about the equation which relates the angular speed and the radius. Then this will become clear. Let's move on to a few mathematical equations. Yesterday I talked about a few definitions which are essential in order to understand the circular motion or to describe it. For example, we need to know what happens when an object moves from a position A to position B along a circle. And this is the center, this is the radius, this again is the radius, this is theta, and this is a certain distance moved when an object moves along the circle. We need to understand how are these variables described and how they are related. This S is known as the arc length. Arc length. This is obviously the radius, and this theta is called angular displacement. So if I ask you to describe or define angular displacement, angular displacement will be the angle subtended at the center by this arc when an object moves from a position A to position B. So arc length is basically the arc length AB, and this angle is the angle subtended by this arc at the center of the circle. So this quantity, which we call angular displacement, simply tells us what is the angle theta formed at the center or subtended at the center when an object moves from a certain position A to a certain position B. So angular displacement is just like linear displacement. Linear displacement means the object is moving along a line from A to B, whereas angular displacement tells us what is the amount of distance covered in terms of angle. And this angle is defined or measured in radians. radians. Angular displacement is measured in radians. What is radian like? So radian is the angular displacement. The angular displacement is 1 radian. If the arc length, is equal to the radius of the circle, In other words, if S becomes equal to R, this theta is exactly 1 radian. So if you are asked to define the radian, you will define it as the angular displacement for which the arc length is equal to the radius of the circle. And one thing that I discussed yesterday was that if an object starts from this position A and comes back to the same position A, it covers exactly 360 degrees, and 360 degrees is equal to 2 pi radians. I should write it to this side, I guess. 360 degrees is equal to 2 pi radians. From this we can work out 1 radian is equal to 57.3 degrees using pi is equal to 3.14, the usual value of pi. Now, angular speed and tangential speeds. There are 2 different speeds going on side by side when an object is moving along the circular path. Angular speed means the rate at which angular displacement is covered. So this is delta theta over delta t. This is how we calculate the rate at which theta is moving. How much angle theta is swept in how much time? For example, if there are 2 pi radians covered in 5 seconds, this will give us the angular speed. The time will always be expressed in seconds, and the change in angle will be expressed in radians, which means in terms of pi. So if one complete rotation, which means 2 pi radians, is covered in 5 seconds, 2 pi over 5, whatever numerical value we have, this will be the angular speed in radian per second. So this is the unit, radian per second. I repeat, angular speed is simply the rate at which angle is varying. So an object is moving from this position A to this position B along the circular path, the angle which is varying at this rate will give us the angular speed. But there is another speed that we need to consider side by side, and that is tangential speed. Tangential speed is a more familiar concept. It is the rate at which the distance S is covered along the path. If this is S, this is obviously measured in meters. How many meters every second is covered is the speed. So this is the more familiar way of calculating speed. If, for example, this is a 5 meter distance covered in 2 seconds, we have 2.5 meter per second as the tangential speed. So while the object is moving along this path, we have this speed, which is known as the tangential speed, which we denote as v. And at the same time, we also calculate how much angle theta is covered in the same time, and we know what is the angular speed. So angular speed and tangential speed are related through this equation. V is equal to R omega. This is very important to understand. Many questions that we'll discuss later on will depend on this equation. We use this equation. V is equal to R omega relates tangential speed to angular speed through radius. I did not erase these two figures because these two are particularly helpful in explaining this relationship. V is equal to R omega tells us if I place a mass at a certain distance r from this axis and rotate this disk, this obviously will be moving, this coin will be moving in this manner with a certain speed v. I call this C1. Let's say I place another coin here. I label this coin as C2. For the sake of simplicity, I assume these two are exactly the same masses, same points, identical ones, but they are simply placed at two different positions. One point, C1, is placed at a radius R1, and this point, C2, is placed at a distance R2 from the axis. So, two different circles are formed now. This is the bigger circle in which point C1 is rotating, and this is the smaller circle in which point C2 is rotating. For point C1, V1 is the speed, R1 is the radius, but omega is the angular speed. Whereas for point 2, V2 is the speed, R2 is the radius, but omega is same. So that means for two different objects placed on a rotating disk will have same omega. The reason for this omega being same is because same angle is covered in given time for the two objects, even if they are placed at two different positions. But due to their different positions, their speeds that we call tangential speed, that becomes different. In one case it is V1, and in the other case it is V2. And you can easily guess which coin will be moving faster. Obviously, with omega same in the two cases, the one further away from the axis will be moving faster. So if an object is moving in a bigger radius, in a bigger circle of radius R1, it must be moving faster even though the disk is having the same angular speed. Similarly, people are at different locations on the earth. If you are at the equator, your omega is same as anyone on any other position on the earth, but because the radius is different, let's say we label this as capital R and this as small r, an object or a person standing here at this position will have a smaller radius of its circular motion. So this must be moving slightly slower in terms of its initial speed. So v will be smaller in this case, and this v will be larger because this has larger radius. After this, we can calculate angular speed. As I did yesterday, I gave a question or two to calculate angular speed to further make it clear. Calculating angular speed. Calculating angular speed. Omega. Suppose this is the Earth and this is a geostationary satellite moving along the rotating Earth. This is a satellite which is a geostationary satellite. Geostationary satellite take exactly 24 hours to complete its rotation, and this is the same time in which Earth completes its rotation on its axis. So if we know the time period that this satellite has 24 hours, that means omega could be calculated using 2 pi over t. You will remember this equation. Omega has a relationship with the time period of any object. If we know it is taking exactly 24 hours to complete its circular motion, complete round trip, then omega must be 2 pi over this time expressed in seconds. So this means 2 pi over 24 into 60 into 60. So this will be its angular speed in radian per second. Another simple example is that of a second hand of a clock. This is a clock with 12 hair, with 3 hair, with 6 hair, with 9 hair, and this is the second hand of its clock. The time period for this second hand is exactly 60 seconds. So you can easily guess what omega is going to be for this second hand. The tip of it, or this point on this, or this point, they will all be moving with the same omega. So omega for the entire second hand on this clock will be 2 pi over 60. And this will be radian per second. Another question in which we use the equation V is equal to R omega. Suppose we have a disk, and this disk is rotating in this manner about its vertical axis, and its radius is exactly 12 centimeters. This is the radius of the disk. And there is, let's say there is an object placed here. If I ask you to calculate frequency of this object, I must inform you about omega. This is 4.7 radian per second. This is given. Omega for this disk is given to be 4.7 radian per second. What will be the frequency of this rotation? You will be using, as I use this equation here, another equation, omega is 2 pi f. This is the frequency which tells us the number of rotations this disk is undergoing every second. If I multiply that number by 2 pi, it becomes angular speed. We later on will refer to it as angular frequency as well. So angular speed will become angular frequency in the coming chapters. The idea is same. This frequency means if I use 4.7 here and divide it by 2 pi, this gives us the rotations per second. How many times this object completes the round trip. So number of rotations per second is this quantity, which is expressed in hertz. But if we are asked to calculate the speed of this object, which is at the extreme end of the disk, this will be calculated using V is equal to R omega. The important point to remember is that the object here will have the maximum speed, because this will be the maximum distance of it from the axis of this disk. If I place this object closer to this will not be the maximum speed, this will become smaller than the maximum value. But V max means we have placed this mass at the extreme end of the disk. So if I rotate with this value of f or with this omega, the max should be this 12 expressed in meters as 0.12 meters into 4.7 radian per second. So this answer will be expressed in meter per second as the maximum speed of the object. So I have shared with you all the worksheet in which all these things are also discussed. I have included these questions in the discussion, so it will become easier this time for you to follow everything step by step. And I hope you will attempt a few more things on your own. The worksheet that I have already given to you will be discussed again in the next lecture, hopefully tomorrow, and that will be completed in this manner. So we are going step by step now. I have tried to move slowly this time so you understand more clearly. Thank you.